Hello, everyone. This is Ziad Sabah. I'm the moderator of this session. I'm happy to present Andrew Green, who is the Managing Director and Lead XVA Quant at Scotiabank in London. He's the author of XVA Credit Funding and Capital Valuation Adjustments, which is published by Wiley, and also co-editor of Landmarks in XVA, which is published by Risk Books. And he's also the co-author of a number of technical articles on XVA in recent years. And without further ado, I'll pass it on. I'll pass it on to Andrew.
What I'm going to talk about today is a piece of work that I've been working on with a number of colleagues at Scotiabank for the last few years, and it relates to our XVA platform. And the presentation is entitled Deep XVA. So what I'm going to do in this presentation, just before I move on, there's a small disclaimer here that I'd like to read, and there's some legal notices at the end of the slide deck. So what I'm going to talk about today is I'm going to start by introducing XVA and XVAs, and then I'm going to move on to some basic background about how XVAs are calculated and the computational cost associated with them. And then I'm going to talk about deep learning and how deep learning fits within our broader platform and how we've applied and built deep learning into our XVA stack as a method of valuing derivatives. And then I'm going to pull it together and talk a little bit about XVA sensitivities in deep adjoint XVA. And then I'm going to conclude the presentation and be open for questions. So let me start by talking a little bit about XVA. So this application of deep learning embeds deep learning within a quantitative finance platform that's used to calculate what we call derivative valuation adjustments. And these are valuation adjustments to a portfolio of derivative trades that are made to account for risk factors that are not typically included or you're not able to include them in the underlying valuation model. So for derivatives, we have valuation models that are applied to each individual derivative, but there are things that there are factors that can only really be calculated at portfolio level. We have a large number of different XVAs reflecting those different risk factors. One example is CVA, which deals with counterparty credit risk, the risk that the counterparty and yourself might default. Funding costs, which are how you actually fund the derivative portfolio. MVA, which relates to initial margin. Many derivatives are now cleared through central clearing houses in the aftermath of the financial crisis of 2007 to 2009. And so associated with that initial margin is some funding costs, and that's what we call MVA. And then another factor is capital costs. And many banks now factor regulatory capital into their pricing of derivative transactions, and hence we call that KVA. So all of these effects typically apply at portfolio level. You can't apply for various reasons. You can't calculate these things at the level of individual transactions. Now, all of these XVAs can typically be formulated in this kind of format, which is essentially a time integral over something which we call an exposure profile, E in this equation 1. So there's various different types of formulas. So it's essentially a time integral integrated over some probability density, multiplying over this exposure profile with some discounting that goes into it. And this little table describes a number of those four basic XVAs that I illustrated on the first slide. And you can see that they have different forms. The density function has slightly different form, and the excitation is taken over a different quantity. So in the context of CVA, this is done over the maximum, the positive value of the positive value less any collateral and 0, which reflects the exposure of the counterparty to you. at the bank. For XVA, it's slightly different. It reflects the total value of the portfolio, expected sum of the portfolio value over time, less any collateral. An MVA is the expected initial margin as a function of time, and for KVA, it's the expected capital cost, or expected amount of capital required as a function of time. So how do we calculate XVAs? Well, there are three primary steps to the calculation. We have a model and we need to calibrate it. Then we need to calculate the expected exposure profile, and then we perform that numeric integration over the exposure profile. And you can see an illustration of how that looks on this graph, on this flow graph. And the key point is that to calculate XVAs, we use Monte Carlo simulation. So we have a calibration step, and then we initialize our Monte Carlo simulation, and then we break it up into a large number of Monte Carlo paths that we evaluate through a number of time steps to the maturity of the portfolio, which we then average to get the expectation, and then we perform that XVA integral at the end. So this is a very simplified graph of what actually happens, but it gives the main concept. To calculate the expected exposure, what we do then is we run a Monte Carlo simulation, and then at every time step and on every path, and if we reflect back on those expectations, what we actually need to do is to value every derivative in the netting set at every time step and on every path. Now, derivative valuations can be relatively inexpensive, but they can also be very expensive because of the complexity of the model required to value the derivative itself. So once we've done that, we apply any operator such as the max function at every path, and then we average at every time step to generate that exposure profile. And here's an example of an exposure profile for an interest rate swap, and you can see that it rises very quickly, and then it has this kind of zigzag or step function behavior, which reflects the structure of this particular type of transaction, which has a number of cash flows that occur at periodic intervals, and the exposure typically declines as those cash flows get paid out. So, what's the problem with this? Well, it's Monte Carlo, and there's a reason we have to use Monte Carlo typically for XVA, because it's a very high-dimensional calculation. We have many asset classes. You could have, fixed income, FX, equity, commodity derivatives, and multiple currencies, all in the same netting set with a given counterparty. Across your entire portfolio, you could have many trades, but even for a single netting set, perhaps one with a clearinghouse, you could have as many as 10 to the 5 to 10 to the 6 individual trades, and then you can multiply that by the number of, then you have a large number of counterparties as well. So the trades themselves can run for many years, and in particular, interest rate swaps and inflation swaps can go as long as 50 years in maturity. You have many time steps. To get accuracy of that numeric integration, you need to have a reasonable number of time steps. So you can have at least order 10 to the 2 time steps. And to get accuracy on your Monte Carlo simulation, you're going to need at least 10 to the 4 Monte Carlo paths, perhaps also with some variance reduction. So it very quickly becomes apparent that just to get the basic XVA value, you need to perform 10 to the 11 trade valuations. And then on top of that, because XVA is a quantity that we don't just calculate the value of, we also actively manage and risk manage within a bank, then it also means that you need to have sensitivities to all of your inputs. And given the high dimensionality, that's very easily 10 to the 3 or 10 to the 4 different input market data points, reflecting points on a volatility surface, inputs to yield curves, FX swap rates, equity swap rates, etc., etc. So if we were to then calculate the sensitivities by the classic finite difference approximation technique, you'd require the basic XVA calculation to be repeated up to 10 to the 4 times just to get the sensitivity. So that's 10 to the 4 times 10 to the 11, which rapidly ends up at 10 to the 15 trade valuation. So clearly that is a massively expensive computational problem. Given even with on CPU, a classic valuation routine might still take tens of milliseconds to run for even a simple model. So it very quickly becomes a massive computational problem. So how do we deal with that? Well, there's two ways, and then I'll talk about how deep learning fits into this picture. But there's two ways that we've followed close to that. One is to use GPUs and GPU cards. The reason for that is that GPUs have thousands of cores. They're highly suited to Monte Carlo as well as deep learning. And one GPU card typically has the performance around about 10 to the 2 to 10 to the 3 GPU cores. And we've also used AAD, Adjoint Algorithmic Differentiation, to calculate sensitivities. And what this means is that if you use AAD, which is a specialist technique, you can calculate all first-order sensitivities in around 10 times the basic forward calculation. So instead of it taking 10 to the 3 to 10 to the 4 times your basic XVA cost, it will probably cost you about 10 times, which is obviously a massive performance improvement. So these are two ways that you can obtain the kind of level of performance that you need to get all the first-order sensitivities that you need to manage the book in a realistic time frame using a relatively small compute grid. But what are the consequences of that? Well, the first thing is that if you're going to use GPUs, then you have to write the code in CUDA, typically. And you also have to do AAD, so that means you have to do AAD, you have to use AAD support libraries and write your code in such a way that it can use AAD. So in a typical bank, we've got hundreds of different types of derivatives, and each derivative will have its own valuation model. And for common trade types, you can have tens of thousands of examples. So interest rate swaps, for example, you would have tens of thousands of those. However, and therefore it's relatively, coding up a model for that is a cost-effective exercise. However, for some less common trade types, you may only have a handful of examples where the trade is a very bespoke trade to deal with particular client needs. And then it becomes very expensive to hand code every type of rare trade into CUDA. And the other problem is that those highly structured trades also tend to come with very complex valuation models. And it becomes difficult to build models that are suited for GPU, simply because the code is quite large, it becomes difficult to code into CUDA, and perhaps the complexity makes it difficult to achieve the kind of efficiencies with CUDA that you would like. So, is there a different way? Well, yes, and that's where deep neural networks come into the picture. Because what deep neural networks do is they allow us to use function approximation for each of these derivative valuations. So in other words, instead of taking the model and coding it into CUDA, we build a deep neural network representation of that model using function approximation and obtain a high accuracy valuation model that has these two major benefits that come for free. The first one is highly parallel inference on GPU. Obviously, the deep neural networks have been, the whole growth of deep neural networks has been driven by the availability of GPU over the last decade. And so that they also work on GPUs in common with our Monte Carlo simulation, and that gives you the benefit of being able to value multiple copies of your trade with different market data or different simulated market data inputs at the same time on GPU. The other thing that comes for free is the sensitivity. Backpropagation, the algorithm that we use to train deep neural networks, is AAD. It's exactly the same thing. It's effectively a symbolic form of AAD. And it means that if you build your XVA platform to use AAD, you can insert a deep neural network valuation model and backpropagate the adjoints that you've already got through it, just as if it were backpropagating it for training purposes. And you get your sensitivities for this model for free. And you don't have to even train the model on the sensitivities to get accurate sensitivities from deep learning, typically. although you can do that. So the first step of this was based on a paper that I wrote with Ryan Ferguson in 2018, which demonstrated that deep neural networks can be used to approximate valuation functions for basket options. A basket option being a derivative with a moderate dimension. The universal function approximation theorem for deep neural networks demonstrates that you can approximate functions to arbitrary accuracy. And why would we do it? We've already seen it fits very well into our platform. The deep neural network inference is much faster than the original model. A deep neural network can run thousands of valuations in parallel on the GPU. On the latest generation GPUs, you have tens of thousands of cores. So you can run a valuation, multiple valuations, many thousands of valuations in parallel. And the overall performance of that inference is effectively millions of times faster than the original model. You've just got a massive performance boost from the original model. The deep neural network obviously can provide those sensitivities, and a deep neural network framework can also be generic. The other advantage is that the DNN is effectively writing the code for the model in CUDA for you, so you don't have to handcraft that CUDA at all. The deep neural network is effectively writing it for you. So what's the cost of that? Well, you need to train those deep neural network weights. That requires a large training set of data, and that must be generated. So what we have to typically do is to generate a training set of inputs for appropriate inputs for the model, run those inputs through the original model to generate a value, and then once you've generated millions of training examples, then you're in a position where you can train your deep neural network to reflect the model itself. Now, that sounds expensive, and certainly I think in the quant finance community that sounds almost impossible, but it really isn't. And why isn't it? Because generating this training data is a one-off exercise. You only have to do this once. It's offline, so that means that you can use CPU cores. You could use public cloud for this. You could use low, periods of, it doesn't have to be done on demand. You could use low-cost periods. You could use scavenging for this. You could use all kinds of different ways of generating this training set, which you're only ever going to do once. And in fact, cloud hardware, multi-core cloud hardware could generate that, a reasonable time training set, in a matter of days without too much trouble. And then training the deep neural network itself has to be performed, and that's going to require GPU, but typically cloud hardware is available for that. And again, it's a one-off exercise, and it's offline. So once you've done it, once you've trained your model, then you can plug it into your XVA platform. So how do we do that? Well, the deep neural network it basically replicates an existing model. So it's got the same set of inputs to the model. You will have to do some things, like you will have scaled your inputs to the deep neural network. So obviously when you perform inference, you've got to scale the inputs so that they fit what's expected by the model. You may have done some dimensional reduction on the inputs, because typically, for convenience reasons, a derivative pricing model may have some redundant inputs that are not absolutely needed, and hence there are some symmetries that can be exploited to reduce the dimension. Some of those inputs will be floating point inputs, some of them will be categorical, and on the input side and on the output, you might have a single output. For example, a value, but you could have more than one output. You may take advantage of multitask learning, for example, and the output itself will also need to be scaled, because it reflects a generic pricing model, not your trade. So you probably need to multiply it by the notional, and maybe some other factors too. The inputs you can categorize in three different ways. You've got some inputs that are constant and reflect the trade parameters, so they are the same at every single simulation point and at every time step. You've got time-dependent parameters, for example, trade maturity, As you step forward in time, the maturity is a shorter and shorter tenor. So therefore, those time-dependent parameters are different at every time step. And then you also have the stochastic inputs, the path-dependent inputs, such as market data, that will be generated by a Monte Carlo simulation, and that is different at every time step and every Monte Carlo path. So, what do we do in practice? Well, you generate a big matrix of your inputs. You have one row per path. You feed that big matrix into your deep neural network, and then what you come out of that is a vector or a vectorial matrix of results that you then integrate into the rest of the valuation models for your Monte Carlo simulation. What do we do? Well, we do it on GPU. Compute is cheap on the GPU, but moving data on and off the device needs care. So what we do is we co-locate the Monte Carlo simulation and the deep neural network on GPU, so they're in the same memory space, and therefore there's no additional cost associated with taking the generated Monte Carlo simulation data and feeding it into the deep neural network. And then for the adjoint, again, we use that propagation. We feed the adjoint. So what happens is, because this is a fully integrated AAD platform, you will have adjoints that will be propagated into the trade valuation step from the steps at the end of the calculation. As you propagate them backwards, you just feed those through the deep neural network in exactly the same way that you would feed it through a CUDA model that's got adjoints, and propagate them through the network, and then we don't update the weights. We're just using this to obtain sensitivity. And then once the adjoints are fed back into the Monte Carlo engine, then they've integrated seamlessly with all of the other types of trades that can't use traditional models. So that's the end of the presentation. So I'm open for questions. This environment is in production. We have a number of trade types that are live on this platform already, and we are steadily going to be expanding the product coverage over coming years as we extend the coverage of the platform to cover all the different types of derivatives that we have in the portfolio, and also to reflect as new derivative trade types become available or structured or new models develop, then we can use this as a way of getting those models onto our XVA platform for XVA calculation. There's a little bit of bibliography at the end of the slide deck, and then there's some reading notices. So I'll stop there and await any questions. The question is, can you walk us through VNN methodology using an FX forward, for instance? Okay, let me try to do that. So what we would do with an FX forward, is a simple trade type, is we would start by training the deep neural network itself. We would take our FX forward model, and we would generate a large set of inputs for that FX forward. Now, typically that would be FX spot rates and interest rates reflecting the two currencies that go into the FX forward. We would then, once you've generated that training set, you would feed that into your model to generate, into your original model to generate the values, and then you would use that training set to just train a deep neural network using simple regression model with your inputs. Then what you would do is you would then build that into your network, into your Monte Carlo simulation. So your Monte Carlo needs to be able to generate the same state variables that are required as inputs to the deep neural network. So that might be the FX spot and the two interest rates. And what you would do then is you would use your Monte Carlo simulation. You would have some state variable generators that generate those state variables on every Monte Carlo path and time step, and then you would feed that into your network for forward propagation through the network to get valuation, to get capacity forward to value the trade, and then you would integrate that and aggregate that alongside all of the derivatives in the portfolio. And in doing so, then you get your expected exposure profile and feed it forward through into those numerical intervals at the end. And then when you're using the adjoint technique, you seed, we call seed the outputs, which would be the CVA value, for example. You then back propagate that through the calculation, right through into the trade values themselves. Then once they're taken from the trade values, we then back propagate that as the output through the deep neural network in that propagation to the adjoint, take the adjoints off the inputs and then feed them through the rest of the into the adjoints for the Monte Carlo, which then back propagates at the beginning of the simulation and generates the sensitivity, and that's how it would work. Then the next question is, what types of product can be treated this way, specifically exotic ones with optionalities? So for that, in that case, so you could essentially treat any type of product with this. Obviously, it becomes more complex the higher dimensionality of the product. So you know, for something simple, for an FX forward, we wouldn't use a deep neural network, for example, because it's too simple. But you might want to have an option. There, you'd need to feed in volatility information. You might even require more than one vol surface. So then you might need to think a little bit about how to structure your deep neural network in order to to keep it at a reasonable size. But in practice, anything could be done. Although with some particular types of structures, it is going to be more challenging because of the, where you've got a variable number of inputs, for example. So a basket option, you've got, say, a model. You might build a model for 5 inputs, but then you might need to deal with 6, 7, 8, 9, 10, however many inputs. You need to structure your deep neural network in such a way to manage that. And next question is how the deep neural network approach will deal with the eyeball transition. Well, in that case, you need to, if your model changes. So in some cases, the eyeball transition is not going to affect directly the models themselves, right? In which case, the deep neural network will be unaffected. In some cases it would, and it does affect the option structure, in which case then you would need to, if you change your model, then if you're going to use the deep neural network, then you need to retrain your model to reflect that.
Thank you, Andrew, very much.
We've got one more question. Time for one more question. So, do you need to train different models for different trade types? Yes. You do. Can you generalize a model? Yes, you can. You could. It's really about the structure of the network and how you fit and how general you can make it versus it's a trade-off between making the model usable versus having to train too many models. So basically, it is a trade-off to reflect different features of the model as to how many models you have versus how generic you make the single model.
All right. Thank you, Andrew, very much. Thank you for the great session. We apologize for the quality of the sound. The recording will be edited, and we will do our best to make the quality better. So thank you for the audience who attended this session. Have a good one.